time ago that the computation of um, cohomology, sheaf cohomology could be done using software called Macaulay 2, and it's very easy to get access to it. Now, just Google Macaulay 2, then the first one is this one. So you can actually try it out here. One server in Melbourne, the other one in Georgia Tech, and we could try to see what it looks like. And you will let's do such a thing. Let's do computing some cohomology of projective sheaf over projective variety. So let's say first we have um, a polynomial ring of variables a, b, and a, b, c, d. So it's just a polynomial ring over rational numbers q and like four variables, and I is some ideal. This is a monomial curve ideal of let's say degrees 1 and 3 and 4. So this is ideal looking like this. You can easily read what it is. So something like this. Now I have the coordinate ring, and X is the proj of this ring. So you have a projective variety over it. Now you do have a projective variety defined by this ideal, and you can easily see that this ideal is a homogeneous ideal. So you do have a projective curve in P3. So because we have four variables, so this is in P3. Okay, so I'm gonna define a sheaf. Let's say this is a sheaf which is I tensor with our R. And this tensor is over the ring of S. So we are going to have a sheaf. Then this is a coherent sheaf. And we know that the cohomology is the first cohomology is the first extension group from the structure sheaf, which is OX, and to that target. And what is this thing? This is like this one. Okay, 1 second. I shouldn't have this. I should make this first a module. Then this is not a trivial sheaf. So if we don't make it a module, you see that this is image of 0, which is 0, and we shouldn't have any cohomology. Now, this time, if I make it a module, which means that R module, then this is not a trivial sheaf. And let's say, what is the first cohomology of that sheaf? Now, you could actually compute it, and this is the cohomology of dimension 12. So you are actually able to compute the sheaf cohomology of some coherent sheaf over some projective variety. This is done by Macaulay too, and I want to mention that this is something quite interesting. And now we are developing. Hopefully, the package will be released this month or the next. I want to say that there is also a package developed to compute the hypercohomology, which is the hyper extension group of some complexes instead of only we have some coherent sheaves. So if you are interested in the computations in algebraic geometry using Macaulay 2, I'm very glad to say something And I personally develop a package which is called homology. So this is done by me, and this is my colleague to package compute for the computation of representation homology. So later on, if you are interested in any of those things, I'm very glad to discuss about it. Okay. I'll stop sharing about this thing. Any questions about like what I have promised for the computations? Comment or questions? Um, yeah, so sort of a unlucky thing that my colleague only could do some commutative algebras, but the functionality is growing, so we can expect it will be doing some non-commutative things in the future.
Can I make a quick comment? Actually, one of my colleagues at the Wake Forest, Frank Moore, he's developing package for doing more complex
Yes, of course.
non-commutative.
Um, Professor Frank Moore is one of the main developer here. So let me go back to my colleague two uh, page. So um, there are a lot of packages here. There is one called DG Algebras, which is now still developing by Professor Frank Moore. So yes, this is the one of the thing that I am very interested in, and I hope at some point some other people will develop a package to compute some simplicial commutative algebras or those kind of things, which is used inside uh, derived algebra geometry. Anyways, yes. Thank you, Professor Wang, for the comment on this. Okay, so let me start. The main thing here today. Okay, so I have this one, and today my um, presentation will be the last section of the first part of our textbook, which is a very quick view of Motivic spaces and Motivic spectra. Spaces and a Motivic spectrum. So what we're going to use is to like bring algebraic geometry and algebraic topology together. More precisely, homotopy theory together to have something. So we haven't really get into that deep, but one of the main thing for algebraic geometry is that all the spaces, all the schemes are very rigid, so that you cannot really perturb them, and because of this, homotopy theory is not quite cannot be quite used in. I'll just say simply be used in inside the field of algebraic geometry. So there should be some new framework to be developed for so that homotopy theory could be used in algebraic geometry. And one of the main thing is called the motivic sort of motivic spaces developed by Vivadisky. And the other one now is very kind of popular, which is derived algebraic geometry. Um, Honestly, I'm not very quite sure, but in a paper by Duggan, I will mention it, which says that the motive A1 homotopy theory could be sort of viewed as a um, um, part conclusion, corollary, or of some universal homotopy theory. And this is supposed to be embedded into the field of derived algebra geometry, but I'm not very sure about it. I don't know. So if you know this thing, please let me know. But I do know what another thing is that rational homotopy theory could be embedded into derived algebra geometry. Okay, so that side we are not going to talk about. We're not going to do derived algebra geometry, but today we are going to give an overview of the Motivic spaces, Motivic spectra, and this will be like the main topic for the rest of this seminar, I believe. Let's start with some settings. S to be a Noetherian scheme. This is the base scheme, and Sm over S is the category of smooth schemes over S. So it's if you're not familiar with this thing, just to think as is spec of complex numbers, then smooth over C is sort of looking like complex. This is not very true, but you should think of this as like complex manifold. So there is a way that you can understand it, and today we care about this guy, which is Motivic space over S, which is defined to be the simplicial free sheaves over smooth schemes over S, which is defined to be, or the functors from smooth up to the category of simplicial sets. Well, pointed. So you could have an unpointed version, but today we are going to care about the pointed one. So again, the category of spaces is all the functors from smooth schemes over S up to the category of pointed simplicial set. So our goal today is to give some model structures on it, which means that we could study the homotopy theory of Motivic spaces. And we'll give some stable version of the model structures as well, which is like the linearized Motivic spaces, the version of linearized Motivic spaces, and which will be called Motivic spectra. Okay. Any questions before I move on to the details? Okay. Very good. So, because we are in the category of pointed simplicial sets, so there is sort of like tensor product, which is the smash product. No, because the target is simply pointed, simply short set. Then, oh, this is a bad notation. I'm gonna change it. Uh, so let's say you and we. Okay. Uh, then for any x and y in our Motivic space, then x smash product y could be defined as well, which is this is also a functor from smooth orb to the category of pointed simplicial sets. Then for any smooth manifold W, it should be mapped. It should map to XW smash product with Y of W. How do you think of this? This is looking like the tensor product. So um, pointwise tensor product. Now we know that there should be a tensor homojunction, and which means this smash product admits a right adjoint will be called hom underline the hom over ms. This means that conclusion, let's say, ms is a closed monoidal category.
Wait, what is the internal home here? Like, how do you define it?
Um, well, um, so okay, you do it pointwise, basically.
Oh, okay. Okay, I
You
see
you
what.
do it basically pointwise. Uh,
Okay.
does that make sense?
Yeah. So point-wise, this is closed monoidals, and you take the point-wise internal home here,
Uh-huh.
right?
Uh-huh. Right. So you see that there are a lot of things done pointwisely, and there should be a model structure pointwise on it, and that is true. But that model structure somehow is not what we really want. Please don't ask me why it's not, because I'm very far away from being an expert here, but the conclusion is no, that's not what we really want. And the reason is sort of like that model structure does not have all the the weak equivalences that we should have. So we want to impose more weak equivalences on it. And how to do that, how to give more weak equivalences. And this is a technique which is called the localization. So localization, but I'm not going to really talk about what localization is. I'm going to give all the concrete definitions here in the Motivic world. Um, so one sentence is projective model structure, which is the pointwise model structure, is not what we want. So how to do it? to fix it. Localization. And let me just throw out the definition. A space X is well, when I say space, it's always the Motivic space. It's called local vibrant if the following is satisfied. So first one is X of nothing is the point. So it preserves the base point, which is, well, basically nothing. Then for any W inside the smooth over S, X of W is vibrant in the sense that this is in pointed simplicial set, and in the Quilling-Kong model structure, this is a vibrant object. The third one is the most interesting one, which is for all pullback squared, we have this kind of like pullback square inside smooth over S, where the phi map is etal. I is an open embedding, and so that phi of z minus u, this thing, to z minus u is an isomorphism, which means that a way of the embedding, this etal map is just a one-to-one correspondence. This is an isomorphism. Then, whenever this is a pullback, this is a pullback diagram inside smooth. Then applying by X gives a homotopy pullback. So, which means that this X, the spaces that I care about, sort of preserve the homotopy equivalences. So if let me recap the definition again, which says I give a bunch of axioms on it. Look, point-wise, it's a vibrant, and sort of we preserve the homotopy equivalences. Then I say this is a local vibrant object in the category of motivic spaces. And I want to point out as well.
Thus the square will be, the arrows in the square will be flipped, right? Because it's
Yes, exactly.
okay.
So, which means that the Z part is the homotopy pullback of the others.
Yeah.
Let me change the color. How can I change the color? I don't know. Anyways, yeah, of course. Okay. Sorry about that. I'm gonna just point out that this thing does have a very famous name, which is called this Motivic sheet goes up to homotopy. From the name of it, I presumably this should be coming from number theory, but I'm saying I'm very far away being an expert in this. So if you know why we care about it, please let me know, and I'll be very happy to hear about it. Okay, so this way we could define the local fibrant object. Now the next one is to define the local equivalence. What are the local equivalents? A map definition. From X to Y is called local equivalence if the following is satisfied that um, for all local fibrant object C, our mapping space applied on it, now this time from Y to mapping space of X to Z. Okay. This is a pointwise equivalence. And another definition is that a map is a local cofibration if it is a pointwise cofibration. So we sort of have all the equivalences, all the fibrations and cofibrations, and you really should say, okay, there is a model category on it, and conclusion, yes, of course, theorem. I'm not really saying this is a theorem because I didn't really define it, but there is a local model structure um, defined above. Any questions about it? So let me recap it. So we have pointwise model structure. Then we add some equivalences, weak equivalences. Then this is a local model structure. And you see from the second definition on this page that the cofibrations does not change. So the category of, sorry, the set, the class of all cofibrations does not change. And this is called the left Boesfield left Boesfield US localization. The right one does not change the class of fibrations, and it's like also using mapping spaces, but in another way. So you do have a right versus left both field localization. And this does the thing that you add some more weak equivalences and produce you a new model structure on your category.
Yeah, before you move to the right one, I just want to make sure. So you already had the point-wise model structure, but you want to
Yes.
upgrade. So for that, you are only changing locally vibrant objects. Is-
Um, so let me say, let me make it a black box. So I do have a model structure which is
Yeah.
pointwise. I add more weak equivalences. I do not change the cofibrations. So the fibrant object should change as well.
And the locally vibrant object that you defined in the last page,
Mhm.
exactly the change, right? Uh,
Yes, yes, yes. It does change. So
I see. And how are you changing the weak equivalences? So, oh, never mind. Usually, weak equivalences are not preserved under home, internal home. Is that the
um, it's still not true that equivalences are preserved by internal home, but I say, okay, they are preserved by the internal home into a local vibrant object. So
Oh,
that's the way
okay.
how I change it.
Okay, okay, internal home for all the local vibrant objects.
Yes, yes,
Okay,
you see that my target are chosen to be the local vibrant object.
okay. Yeah,
So basically, um, we are not really changing the equivalences, but we are changing the object that we care about from vibrant object to local vibrant object.
I
And and
see.
in another way, we say that the model structure is study the homotopy theory on the vibrant object in your category.
Okay, okay.
Does it make sense?
Somewhat, yeah. This is my first time like trying to see, so
Localization this
yeah,
way. Yeah.
yeah.
So uh, last week, Colton talked about another localization, which is called Gabriel-Zisman localization, if um, I remember the name correctly. That one, the construction is totally different from here. They are just very different. But
Oh,
because one thing is that they are both called localization. They have some relations, and yes, of course, they do have some relations. But again, so both field localization does not change the category. It changes the model structure on it, left or right. However, GZ, Gabriel Zisman localization, changed the category on it. So does change the category structure on it. It doesn't care about the model structure. It just simply changed the category structure on it.
I see. And that Gabriel James Zeman localization was, to take the zigzags, right?
Yes, using the zigzags. And in some special case, it is equivalent to the roofs.
Yeah, the one that Colton showed. Yeah, yeah.
Mm-hmm.
I see. Okay, go ahead. Yeah.
Any questions? Um, Again, before I move on to the next one, I really want to point out that the localization, all the things about localization really rooted a long time ago. And this post-field localization, from my understanding, it goes back to the year of 50s when Sear introduced um, he called a Sear subcategory, which is again a sort of localization as well. And the purpose of Sear's construction is to compute the finite generated property of the homotopy groups of spheres, and that's kind of like very um, how do you say, the one of the main work that he got his Fields Medal, and after that, there are a lot of other versions of localization, like Vadir localization. It could be viewed as the sort of both field localization in the world of triangulated category. It's not, again, I want to say like Sayre's localization is different from Gabriel's localization, but it is very similar to this both field localization because it is changing the extra structure on your category instead of changing the category. Although Sayre localization does change the category a little bit. So, Professor Hoffman, you seem like to comment on.
No, I wasn't going to say anything about that. Let me just ask you one question.
Mhm.
This theorem that you're quoting, the quote theorem, whose result is that?
Yeah, well, I should say it is the both field localization. I'm
Yeah, I know,
quoting.
but who proved it?
I don't, well, honestly, I don't know. Honestly, I don't know. I think this should be credit to both field, but this is not something I didn't really track to the main, the original reference. And
Okay.
I'm not sure. Sorry about that.
Okay, that's all.
So and also like because there are so many like literatures talking about localization, then this is one of the main thing, and I'm personally very interested in it. So again, I'm happy to discuss it if you are also interested in it. Okay, so this is the part that we introduce local model structure on the space of Motivic spaces, sorry, the category of Motivic spaces. And there will be another one that's, as I promised, which is you have a sort of like internal interval object in algebra geometry. A1 plays the role of interval object. So we want to use this guy to define a model category on it as well. So very similar. We have this definition, and A1 fibrant object is a locally fibrant object X such that you apply an A1 product with something, then because you have an embedding, let's say you have an embedding W to W cross A1, then apply X on it, then you get the inverse one. This one is a pointwise fibrant, weak equivalence, sorry. So A1 fibrant object is some space so that for all the locally fibrant thing, it doesn't change the homotopy on it. Which means that W to W cross A1 is a homotopy, and X applied on it is also a homotopy. Equivalence, sorry. I would say equivalence. Which means our target, sorry, our focus is really the spaces does not change the A1 homotopy.
Wait. Are you assuming that W to W cross A1 is a weak equivalence, pointwise weak equivalence, or are you assuming that it's a
I'm
homo?
saying we should view this as a homotopy equivalence because, in algebraic topology,
Yeah, that's
product by interval object is equivalence.
true.
So this really should be viewed as equivalence, and we care about the spaces does not change the homotopy equivalence. Does that make sense?
Yeah, but the notion of homotopy itself is not very clear to me yet.
Yes. Wow. So we are imposing some homotopy equivalence on it. So it's like it's not naturally arisen. I'm not sure, but
Okay.
um, I think it's very useful, but I can't really answer why it is useful. Meaning, I don't know what kind of problem it really solves. But I do believe that this is very useful. And likely, um, and very likely that definition and A1 weak equivalence is a map x to y, so that for all A1 vibrant object Z, this internal harm Ay to Z is the same as, I'm gonna explain it a bit later. And the third definition is cofibrant is the local cofibrant. Again, we do not change the cofibrations. This just occurred to me that I am a little bit unsure about the left hand side or right hand side, which means that, well, I don't know if I say it correctly. This should be left or right. I'm gonna put a question mark on it. So one way or another. So I'm very not sure about the left or rightness of it. So if you see the literature that it is just the opposite of what I'm defining it, it might it's likely that I'm making something wrong. So again, now I should make some changes to the previous one that it's a bit not true in the sense that I need to take the replacement of it instead of only have the okay. So let me just jump to the okay. Here I have A1 vibrant object on it, and I'm going to define A1 equivalences on it. So now here there is a point that as Crescendo pointed out, it does not preserve the homotopy equivalences. So I want to impose the condition that it preserve the homotopy equivalences on it, and by doing that, we need to do the derived functor version. So it should be replaced by a suitable replacement. That's the way how we think about it. And the way we do it is say, okay, if I have a fibrant. This is cofibrant object, if I'm correct. Yes. Okay, so there is a factorization functorially. There is a factorization. And we
I think it's the other way, from X to terminal object.
no, I want this one. I want this one. No, I do not want the other one. So I have two functorial replacement.
Yeah. Then it's a cofibrant replacement,
There
not
is a
fibrant.
cofibrant. This is a fibrant. I want this thing. I do want this one. Yes, of course.
So in this, what is your weak equivalence? Is Kx weakly equivalent to X?
No. Yeah, this is defined. This is the definition. So here I have a map from X to Y.
Yeah.
Then I have a map induced from Kx to Ky.
Yeah, true.
So if this map induces A1 induces equivalences to every Z, then we say that this is equivalence.
Okay, but you have to say what K is, right? What is your Kx?
It's a choice. There is a functorial factorization. I don't know which one, and I don't care which one.
So you are saying that like your start to Kx that can be weak cofibration, there's trivial cofibration. Also Kx to X can be trivial fibration. Doesn't matter to you.
No. This is this. Okay, so this is by taking replacement. So how do you think of it? You think this as a hom, and well, let me have another one. So you have hom from let's say X and Y. This is this is the thing, but this is not the correct thing. How do I get the correct thing? The correct thing is R hom from X and Y, and this guy hi of R hom could be done by hom applied onto something projectively to X and computed on Y, then you take the homology on it. So this P is looking like your Kx over there. So this is a project resolution, but it's a project resolution which is equivalent to your original object. So this one has to be a weak equivalence.
Yeah, but in this case, this projective resolution is also your cofiber replacement, isn't it?
It is the fibrant replacement.
Five.
Yeah, wait.
Fibrant, right?
This
Because
is this is a cofibrant replacement. Yes.
I'm saying, so your K is your cofibrant replacement for your X.
Yes.
That's the point. Okay.
Yeah, that's the point. So, very likely just to think hom as ext, then every other thing works. Okay. So, any other questions? If not, as I said, I have fibrant object, I have fibrations, I have equivalences, and again, I do not change the cofibrations. Again, the theorem says that there is a this gives a model structure on the Motivic spaces, and the point is this is this is the so-called A1 model structure is equivalent to the so-called unstable homotopy category defined by evil yes. So now this is the category that we care about to study the motivic spaces. But the unstable version, any questions? Any questions? Okay, good. So you see that there is a word, there is a word unstable. So there should be a stable version as well. And how do we think of it? If we have spaces, then this is sort of unstable. If we have spectra, this is equivalent to say this is stable. And stable, this is again saying like the linearization of the unstable one. And you should impose a stable infinity category on it. And it is known that every stable infinity category gives you a triangulated structure. So it is looking like we are studying the complexes of the spaces. So it is really linearized the space, looking at a point to study sort of like the derived tangent space is something. Okay, the next goal is to talk about the stable version of the motivic space. And it is a bit similar, but I want to say a bit more about the motivations. Now we have MS, which is the category of motivic spaces. Then question is to how to study the homology or cohomology on this category MS. To really study it, study the homology or cohomology, it is okay. We care about the stable version of this category. We care about the spectras. So the next thing I'm going to do is to introduce the spectra object on it. Okay, so but first of all, I need to change the category a little bit. That's so we need to change the category. So okay, let's say FMS is the fourth subcategory of Motivic spaces, which is consisting of finite spaces, and F of S is the category of functors from finite spaces to spaces such that X is continuous in the sense that for any A and B of smooth schemes, you have internal from A to B to your functors applied on it from XA to XB. This map is a map of Motivic spaces. So we need to change our target from all the Motivic spaces to the category of continuous functors on it. Then it is giving us a linearization of what we want. Okay, so let me think about how to
Say that again. What is your FMS?
So small fms, this is finite spaces. So
Oh,
this is finite?
I mean, what do you mean by finite spaces? Cardinality is finite also.
Yes, you can define, well, because you can define the finiteness on every point. So you can do it.
Oh, okay.
And continuous means that at each point, at each pair of points, then this functor applied onto the mapping space is continuous. Is not only a map of set, but a map of spaces, so that it is a continuous map.
Yeah, true, but I still don't understand the finite. Like, what do you mean by finite Motivic space?
Okay, yes, sure. So, let's say X inside Motivic S is finite if for each for every U inside smooth, X of U is finite.
Oh, okay.
Good? Okay. So the last thing, I hope I'm not going to going too fast. But okay, so the last thing is like give motivic structure on this target category so that it is giving us the stable version of motivic spaces. Any questions? Good. So again, there is pointwise model structure. The category of FS, because it is the category of functus. This is the category of functus. Now, so again, we are going to do the localization process to get model structure. And HT fibrant, I think, I'm not sure, but I think this HT stands for height. I don't know where this height comes from. It should be coming from some number theory, which I have no idea. But please let me know if you know what this thing is. So a height fibrant object is pointwise vibrant object such that for all A1 equivalence phi from U to W in your finite spaces, then the induced map X applied onto phi is an A1 equivalence, which means we care about those pointwise fibrations that preserves the A1 homotopy equivalences. Whenever you have A1 equivalence, then the height fibrant object maps it to, again, A1 equivalence. And again, similarly, we have definition, which says an height equivalence is a map from X to Y such that, again, your hom from KY to Z to hom, internal hom KX to Z is an A1 equivalence for all vibrant height vibrant object. This is again similar construction. And definition again, cofibration is again pointwise cofibration. Now, apply on that quoted theorem again, we have a model structure. Now, the last thing I'm going to say is that this, yes, the last thing. And the last thing is that the height model structure on F over S is equivalent, of course, to the category of spectras over S. What is that thing? So what is this category spectra? So let's uncover it a little bit. Just this is mimicking what Crescendo did last time to say what a spectra is in the category spaces by changing the category of topological spaces to Motivic space. So a T spectrum So this T stands for Tate. A T spectrum is a sequence E0, E1 to infinity. All these things inside Motivic space together with together with structure map T smash product with EI 2 EI plus 1. So this is very similar to you should think this T is S1 and this is Si. So S1 smash product with S1, it is weak equivalent to Si plus 1. And here in the category of MS, this T is the Tate object GM smash product with spec of S.
What's that GM?
Multiplicative group. So one torus. Just think of this as a one torus.
Yeah.
Okay. GM. If you wish, this is spec of C adjoint with X plus minus Y.
Okay. Yeah.
So, conclusion, we have the motivic spaces, which is MS, with a model structure by A1 model structure. And we have the category of spectra over spectra in this category. We also have a height model structure on FS. We know that this height model structure is equivalent to the category of spectra of motivic space. So this is the linearized version, which is in this page, and the unstable version is 15 minutes ago, I guess. But all these things are the things I want to present, that these are the motivic spaces or stable motivic spaces that we care about in the near future.
Okay. So are you done?
Yeah, I'm good.
All right. Thank you so much for the talk.
I'll stop sharing.